Leah here from leahforsci.com, and in this video, we'll continue with the NMR topics discussed in the last video by applying it to a simple example. Don't let the simplicity of this problem fool you, however. If you apply the same techniques to a complex problem, you will find that you can solve any NMR question provided. In this problem, we are provided with an NMR graph and the molecular formula for the molecule, which is C3H7Cl. Given that this is such a simple formula, we can actually guess at the correct molecule by finding the isomers. 3 carbons gives me a propyl chain, and I can choose to put the chlorine on the terminal carbon or the central carbon. However, let's assume that we do not know how to guess, and instead we'll go through the steps I've shown you to analyze every peak and how it relates to the molecule. The first thing we looked at was the number of hydrogen types within the molecule. Recall that every peak represents one unique type of hydrogen, and given that I have 3 peaks in this graph, I will have 3 hydrogen types. We will now apply the rest of the techniques to each individual peak and see what it tells us about the molecule. Before we do that, we'll analyze the graph, remembering that we called the right side of the graph the boring region, meaning far away from strong electronegative groups, and the left side of the graph is the exciting region because this is closer to electronegative groups. The 3 things to analyze will be the splitting of the peak, the neighbors to each peak, and finally the chemical shift on the graph between the boring and exciting region. We'll start with the peak on the right and count 3 tips on the peak, giving me a triplet. And this means that I have 2 neighbors. Recall the rule n+1 gives you the number of peaks, meaning the number of neighboring hydrogens plus that initial peak. Doing this formula backwards, we will take tips minus 1 to give me hydrogen neighbors. In this case, I have 3 tips minus 1 gives me 2 neighbors. And finally, the shift is all the way to the right, meaning this group of carbon and hydrogen atoms is on the most boring end of the molecule or as far away from the Cl as possible. For the second peak, I count a total of 6 tips, and that gives me a sextet. Using the reverse of n+1, I know that I have 5 neighbors. The shift for this peak is slightly away from the boring region. That means given the chlorine on the molecule, the hydrogens responsible for the second peak are going to be closer but not closest to the chlorine atom. And last but not least, the peak on the left has a total of 3 tips for another triplet. Once again, we have 2 neighbors. However, the shift on this peak tells me it is the most exciting carbon-hydrogen group, and that means the hydrogens responsible for this peak are attached to the carbon that is holding the actual chlorine. Let's ignore the isomers that we've drew for now and see what the information on the graph alone tells us about the molecule. Sometimes you will be given either an integral value or a number of hydrogens represented by each peak. But in this molecule, the only thing we know is that there are 7 hydrogens in total, and we will have to deduce where these hydrogens show up. If we look at each peak and determine how many neighbors it has, we can then reverse what we have to see which hydrogens belong where. If both triplets have 2 neighbors and the sextet has 5 neighbors, then we can assume that the middle peak is responsible for the 2 hydrogens which are neighboring both triplets. I'll keep the colors consistent with the descriptions so you can follow how I'm coming up with these hydrogens. The sextet will be a CH2, and the reason I got H2 is because both the triplet on the right and the triplet on the left each have 2 hydrogen neighbors, so the middle peak will be those 2 hydrogens. Given that there are only 3 carbons in this molecule, and we know the blue carbon is central, we'll draw a red carbon to the right and a purple carbon to the left. The middle carbon has a total of 5 hydrogen neighbors. Given that I have 5 hydrogens left, I know that I have 2 hydrogens on each of the carbons, both to the right and the left. That means that I have my final hydrogen on one terminal carbon and the chlorine atom on the other terminal carbon. The peak to the right is a CH3 group that is a triplet due to being split by its two hydrogen neighbors. The middle group is a sextet, that's the CH2 in the center being split by three hydrogens from the right and two hydrogens on the left for a total of 5. And the one on the left is being split by two hydrogens from the center and also shifted closest to the exciting region because of the chlorine attached. Now let's look back at the predicted isomers, and we can see that the structure we came up with matches the 1-chloropropane and not the 2-chloropropane. Just a quick note about the 2-chloropropane, it is a symmetrical molecule, and that means that you only have two types of hydrogens, and so you would only get two peaks on the graph. This is what I meant by the isomers alone can help you figure it out, but I wanted to show you the breakdown so that you can get not only simple but also difficult problems correct. Are you struggling with organic chemistry? Are you looking for information to guide you through the course and help you succeed? If so, download my ebook, 10 Secrets to Acing Organic Chemistry, using the link below, or visit leahforsci.com/orgosecrets. That's ORGO secrets. If you enjoyed this video, please give it a thumbs up and even share it with a friend or two. If you have any questions regarding this video, leave a comment below or contact me through my Facebook page at facebook.com/leahforsci. There will be many related videos posted over the course of the semester, so go ahead and click the subscribe button to ensure that you don't miss out.